This is section 4.6, modeling with exponential and logarithmic functions. We're first going to begin by solving literal equations. And in a literal equation, we'll be solving for a specified variable. And you'll be told which variable you were to solve for. So in number 1, we are going to be solving for D. So as you can see, we're solving for D. So we'll start moving terms away from D. So let's subtract 23.5 from both sides. And we just need to divide both sides by 2. Now, if we are trying to solve for D, we could go ahead and go into exponential form. So let's rewrite this first, the log of D, and of course that has a base 10, since that's a common logarithm, is equal to s minus 23.5 over 2. So now we can say that 10 raised to that quotient power is equal to D, and that's what we're looking for. 10 raised, and let me move that 10 down. 10 raised to s minus 23.5 all divided by 2 is equal to D. Then we can just write it the other way. Okay. Let's take a look at number 2. In number 2, we are going to be solving for x. So as you can see, there's x. So this time, we are going to be moving terms away from the term with the x in it. In this case, we'll just begin by adding t to both sides. Now, we'll divide both sides by 3. Kind of that looks better. Okay, now we know that if we take the log of both sides, or we go into log form, then we can get this x down to where we can solve for it. So you could think of going into logarithmic form, or you could think of taking the natural log of both sides. So let's just go ahead and write this into log form, thinking about what base we have. We could say that the natural log of this expression, 4.2 plus t divided by 3, is equal to n times x. Okay, now we are just needing to solve for x. So we can say that x is equal to, let's divide both sides by n, and then we have the natural log of 4.2 plus t divided by 3. And these are what we call exact answers, okay? And these are exact answers because we still have this other variable that, of course, we couldn't put in our calculator. So this is how we will leave our answers, our solutions. Okay, next we will look at models for exponential growth and decay. And we're actually going to be creating these models. So how are we going to do this? If we begin with an initial amount of y sub 0, and we are having a variable y change exponentially with respect to time, with respect to t. So how would we write this for a positive constant k or a negative constant k? So for a positive and negative constant k, we will use y equals y sub 0 e to the kt. But here we call it growth when we have a positive k. And here we call it decay when our k is negative. Let's try to create a model in number 3. Suppose that at 19 years old, you win $100,000 playing the lottery. If you would like to have $1 million when you retire at age 67, determine the average rate of return needed under continuous compounding. Okay, so let's talk about this. We first have an amount, and we could use this y equals y sub 0 e to the kt. But we should also be thinking about our exponential growth of money, which is the amount equals the initial amount times e to the RT. So we can see this relationship. So with that, we have P is equal to $100,000. That's how much the principal amount is. We would like the amount after the time from 19 to 67 years, which we'll show as 48. We would like that amount to be $1 million. And we're looking for the rate. Let's go ahead and compute the time. 67 minus 19. So that would be 48. So with this, we have 1 million equals 100,000 multiplied by E. We are solving for R multiplied by 48. So dividing both sides by 100,000, you can see that the left-hand side is now 10. So we have 10 equals E to the 48R. Let's go into logarithmic form. So the base of the natural logarithm is E. And so we have the natural log of 10 is equal to 48R. Now keep in mind we're solving for this R. And so we would have R equals 1/48 multiplied by the natural log of 10. And if we put that in our calculator, we'll have 1 divided by 48 multiplied by the natural log of 10. And we get 0.0479, so about 0.048, or we could say 4.8%. Okay, taking a look at number 4. According to a study published in 2012, Burmese pythons are becoming the new top predator in the Florida Everglades. Not many animals in the Everglades can stand against a python that can grow to 23 feet long and weigh over 200 pounds. 20 pythons were recorded as captured or killed in 1995. By 2009, that number had increased to 378. So we had 23 in 1995 and 378 in 2009. Write a function of the form P of t, so that population that depends on time equals the initial population times e to the RT. So let's take a look. Our initial population is 20. And I wrote 23, and that should have been 20. And the population after 14 years is equal to 378. Now we do need to take a look at that, because from 1995 to 2009, we have 14 years. And I could probably bring all of that, all of that down here, and I could just get rid of that. Okay, so now let's go ahead and write our function 300. I'll write that a little bit higher. 378 is equal to 20 times e to that rate times 14 years. So dividing both sides by 20, we have 18.9 equals e to the 14r. And now if we go into exponential form, we will have the natural log of 18.9 equals 14r. And so we have r is equal to 1/14 times the natural log of 18.9. And you'll come up with approximately 0.21. So now what can we say? Now we can say, therefore, this function, P of t, is equal to 20 e to the 0.21 multiplied by t. So we came up with this function using given data. So we created this function using the given data at both of those years. Now we're going to use the model from Part A to approximate the number of pythons captured or killed in 2017. So 2017 would correlate to time equal to 22, since 2017 from 1995. So you could say, maybe I should have written that. 1995 to 2017 gives us 22 years. That's probably better to write that out like that. So now we could go ahead and say that P of 22 equals 20 times e to the 0.21 times 22. And that's approximately 2,030 pythons. Okay. In C, if the ratio of pythons living in the wild to pythons captured or killed is approximately 100 to 1. So living in the wild related to captured or killed. That's what we're looking at, is 100 to 1. How many pythons were estimated to be in the Everglades in 2012? So for 2012, from 1995 to 2012, we have 17 years. So the first thing we'd like to do is find P, the amount, at year 17. So that's 20 times e to the 0.21 times 17. And that's approximately 710 pythons. And in this case, these are the ones captured or killed. So now we're going to use that ratio and bring that down a bit. And then we'll be able to give that estimate for the Everglades. So now what we could do is we could say 710 multiplied by 100 equals 71,000 pythons in the Everglades. Okay. In number 5, you can see a sample collected from cave paintings on an archaeological site in France shows that only 2% of the carbon-14 still remains. So only 2% of the carbon-14 remains. And now we want to know how old is the sample. So here is the model that we are given. And this is a really important model because Q sub 0 is the original quantity of carbon-14. That's the original. And Q is the amount over time. Okay? So we will use that equation to see how old our sample is by solving for T. Okay, so let's go ahead and do that. We have that if only 2% remains, we have 0.02 multiplied by the original amount. That's what Q is equal to at some time. So if we have 0.02 of what we started with equals what we started with times E to the negative, I'm going to have to move this down just a bit, to the negative 0.000121 t. And this t is what we need to solve for. Well, we can divide both sides by Q of 0, and we have 0.02 equals E to the negative 0.000121 t. And now we can go into logarithmic form, and we can say that the natural log of 0.02 is negative 0.000121 t. And that was a decimal, 0.00121. Okay, so now let's go ahead and solve for t. So t is going to be the natural log of 0.02 divided by 0.000121. And you can go ahead and find that in your calculator, and that will be 32,331 years old. That's how old that sample is when only 2% remain. Okay, now let's take a look at logistic growth. This is when we include some logic, okay? And there are some very important points about using a logistic growth model, but basically it takes into account limited resources, carrying capacities, and such. So the logistic model accounts for limited resources, carrying capacities, etc. Okay, so as you can see here, here is this function y equal to c. We have a horizontal line at y equal to c. We also note a point of inflection, and this is where the rate of change is increasing, and here the rate of change is decreasing, but approaching that value of c. And here is the model. C is going to be a constant along with A and B. So let's just take a look at number 6 and see what we can come up with that model. I'll keep that up. The population of Los Angeles, P of T in millions, can be approximated by this logistic growth function, where T is the number of years since 1900. So that's really important to note. And evaluate P of 0 and then interpret its meaning in the context of this problem. So P of 0 would be letting T be equal to 0. So that would be equal to e to the 0, which is just 1. And as you can see, that would just be 15.589. So maybe I will just let you all see that that's 1 plus 14.589. So that's just 15.589. And that's approximately 0.20488. Now keep in mind that that's millions of people. So that would mean 204,888 people in year 1900 since we had t equal to 0. Okay, use this function to approximate the population of Los Angeles on January 1st, 2016. So 2016 minus 1900 equals 116. So that's what we will be using for time. Okay, so we will now find P of 116, which is 3.194, divided by 1 plus 14.589 times e raised to the negative 0.052 times 116, and that will come out to approximately 3.09 million people. Okay, now let's go ahead and create exponential and logarithmic models using regression. So we're going to use a calculator to input these values and then to try to find the best model to fit that data. So let's go ahead and get this data input. So we will press Stat, Enter, and we can just enter those pretty quickly. And then in the second column, enter those values of y. Okay, and I always like to, after we have those in there, take a quick look, make sure they look okay, and we want to second quit. Now we're going to press the Stat button, and we're going to arrow over to Calculate. So to run Exponential Regression, you're going to press, and of course this is an L1 and L2. We're going to press Stat, arrow over to Calculate, and then we're going to choose Exponential Regression, which is the number 0. And you can see that we have L1 and L2 with our X and Y data, and we are just going to press Enter. So as you can see, the calculator immediately gives us this function, which is y equals a times b to the e to the x. So our function is y equals 2.299 multiplied by 2.718 to the x power. And sometimes it's written like this, and that looks a little bit better. Or I have seen it written like this. So that makes it nice. Now, what could you do? You could go ahead and rewrite that with an E as a base So you could also rewrite this, and I'll show you how. 2.299 times e to the 1.00013x. So how you could do that is notice that e, I'll show you on the calculator, e is second divided by, so that's 2.718. So there you see that this is just e, and then you could write e to and actually, we'll just go ahead and wait on that, okay? So let's just leave this. We can notice that that's E. Let's just leave that like that. Okay, so now let's go ahead and look at number 8. And as you can see, we'll use our calculator again. But this time, we're going to use logarithmic regression, okay? So just like I wrote there, in order to run logarithmic regression, we're going to press stat, arrow over to calculate, and then I'll go ahead and show you where that is. So let's go ahead and put our data in. And so we should just be able to clear all of that. And I'm just going to go ahead and type right over it. So we have 2, 4, 5, 8, 11, 14, and then just press delete there. 3.75, and you can just go ahead and get these typed in. Okay, and then I always like to say second quit, and let's clear our home screen, and here we go, stat, arrow over to calculate, and if you look all the way down to number 9, you can see linear regression, and you can use a plus bx, but that's not what we want. We want natural log regression. And here you can see this nice form, and I forgot to see stat or over to calc. It was number 9. And that's natural log regression. And it actually gives us this beautiful form, which is y equals a plus a constant in front of the natural log of x. So as you can see, we now have a model, and that is y equals 2.503 plus 1.799 times the natural log of x. So there you can see logarithmic regression using the natural log. And that concludes this section.